Welcome back to the Advanced Microcontroller series. In today's session, let us discuss about I2C protocol. It is also called as I2C protocol, Inter-Integrated Circuit, or TWI protocol, Two-Wire Interface, or IC. So these are the different names which having I2C protocol. Different name but operation is same. I2C protocol is a intra-board protocol, means communication happens between the ICs or chips, and it is developed by the company Philips. And here is the agenda: introduction, bus feature, the protocol, bus speeds. Let's see one by one. First is the introduction. It is a synchronous communication protocol. Means here communication happens with respect to clock. So one line is fixed for sure, that is the clock line. And it supports half duplex communication. So it is a two-way communication, but one can communicate at a time. So if it is full duplex communication, then how many data lines required? In full duplex communication, both can transmit and receive, or both can communicate at a time. But in half duplex communication, one can communicate at a time. So here one is going to transmit, other one is going to receive, and other one is going to transmit and one is going to receive. Like that communication happens. So it requires single data line, and it is multi-master multi-slave communication protocol. In previously we discussed about the single master multiple slave communication protocol, isn't it? That is SPI protocol. So SPI protocol is 20 times more powerful than this I2C protocol, but still people prefer with I2C protocol. Why? Because it supports multi-master multi-slave, which is not there in the SPI protocol. So this is about the introduction, and next is the bus feature. Two-line interface. One is the clock line and one is the data line. Total two-line interface. And next is the software addressable and multi-master with CD. So what do you mean by CD? Collision detection. Because there is multiple master in our network, there are chances where multiple masters start communicating at the same time. So this collision detection comes in picture only when multiple masters are communicating at the same time, and in that case there should be some decision making mechanism who is going to be in the bus, because multiple masters, even though they transmit at the same time, because there is only one data bus, only one can communicate at a time. So there has to be some mechanism who is going to judge which master is going to make use of this bus for sake of communication, and that happen with the help of collision detection. If multiple masters start communicating at the same time, only one master can communicate at the given time, or one master can continue to communicate, and that decision is done with the help of collision detection. And it is a serial protocol. Not only this, UART protocol, SPI protocol, I2C protocol, CAN protocol, all are the serial protocols. 8-bit oriented, bidirectional with 4 modes. Next, on-chip filtering. Nowadays, this protocol is so commonly used. The chip comes along with the filtering. There is the presence of chip filtering, and it is just for sake of reducing noise. So these days I2C block come along with the chip filtering. There are the there is chip filtering is available. So that's why nowadays I2C protocol is most commonly used. And next is the protocol. So we are going to see the example. So this is the example. So here you can see there are two lines. One is the data line and other one is the clock line. And these are the two lines for which all the devices are connected. So all the devices has been connected to same clock line and same data line. So here we having so many devices, and out of these devices microcontroller A and microcontroller B. So these two are master capable as well as slave capable. They can act as a master or they can act as a slave. But other devices means LCD driver, double EEPROM, RTC, ADC, temperature sensor, these are act as a slave capable. Now this is a network. This have these many components. So now imagine this microcontroller A as a master. Being a master, it wants to communicate with this slave or temperature sensor. So this is an example how the communication happens. So let's see. Microcontroller A, being the master, wants to communicate with the temperature sensor. So now usually what happens, whoever wants to communicate is going to transmit the unique addresses. So here we having multiple devices, so we have to use something to indicate specifically, right? So there will be some unique ID given to every devices. So this microcontroller transmit unique address to the data bus. So it will transmit the unique address to data bus. Then what will happen? When are going to see that address? All the devices in the network are able to look into the data. So whatever is being transmitted by microcontroller A, all the devices are able to look into the data. Now whichever devices matches that unique address is going to send back an acknowledgement. Microcontroller A transmitted the address of temperature sensor. Now what temperature sensor does? It will understand that microcontroller A wants to communicate with it. Now temperature sensor will understand after getting the unique address, because whatever is transmitted on the data bus is matched to the address of temperature sensor. Now temperature sensor is sent back an acknowledgement saying that I have received the unique address and I understand that you want to communicate with me and I am ready for the communication, and communication starts. Then continue. Once the communication done, master can stop the communication. So whoever is the transmitter will stop the communication. So every device is having its own unique address. The manufacturer of the device is going to give the unique address. So this is how two devices communicate at a given time in the network. This network worked as a two-wired interface. So two-wired interface, here you can see SDA line and SCL line. So there is only one data line, that is SDA line, and there is only one clock line, that is SCL line, serial data and serial clock line. So these both lines, so both of them are worked as a wired AND. What do you mean by wired AND? So wired AND means what? So let's see now. So here we having two devices, device 1 and device 2, and only one data line. Here you can see one data line and one clock line we having, and there can be multiple devices connected each other. There can be multiple devices connected to a same wire. There is transmission happens and reception happens, and at the end what signal is being seen in this data line is nothing but wired AND. So here we having two devices which are connected to each other and one data line. So in that we having two devices. The device 1 is nothing but master and device 2 is nothing but slave. So let's consider this is master and this is slave. So these devices are connected to a single data line, that is nothing but SDA. And here we used one device, that is nothing but MOSFET, open train MOSFET. So whenever I want to write the data, I write it at this particular device. So here you can see data 1 out. So data 1 out, or here we having data 2 out, isn't it? So data out is the one I am going to use whenever I transmit the data. So transmission means what? It is nothing but write, and reception means it is read. Now whatever data you want to transmit, you can write it at the data 1 out or data 2 out. And whenever you want to read, you can read it at the data in. So here we having data in, and in device 2 also we having data in. It should be data 1 in and it should be data 2 in. Okay. So here you can see it is data in. So by using data in, you can read the SDA line, and whenever you want to write, you can write it in the data out. And here you can see there is one pull-up device is there. So, and what is the name? VDD, isn't it? Named as VDD. And right now here nothing is passing, isn't it? So nothing is passing right now. So what we will going to read in the SDA line? So here nothing is passing. So we are going to read 1, isn't it? In order to transmit, what we have to do? We have to pass either 0 or 1. Here right now nothing is passing, right? So what we will read in data in of device 1? 1, isn't it? So whatever is connected, the same it is going to read. So here you can see it is connected to device 1, and in device 2 also we will read the same. So here also we are going to read 1. So if the address are reading 1, that means what? The bus is being idle. If SDA line is equals to 1, then the bus is idle, nothing is being transmitting. So if I am going to transmit, so 0 here, then what will happen? MOSFET turns off. It is been off state. So whenever I transmitting 0 here, half of the part is achieved using the concept wiring, just because of the connection. So now we achieved half of the part, that is wiring. So because of the pull-up circuit. So right now MOSFET, there is no communication takes place. But if I transmit 1 instead of 0, then what will happen? MOSFET turns on. So now the current from VDD is flowing towards the ground, isn't it? you are going to read at the STA line. So right now it is 0. Okay. So in that time current is flowing towards the ground. In that time in the STA line you are going to read 0. Here you are going to read 0. In data in of device 1 you are going to read 0 only, right? And in device 2 also you are going to read 0. But here we transmitted in data 1 out, but device 2 is not even transmitting. Still it's going to read 0. So whenever devices are reading 0, understand that there is a communication happening. The bus is not been idle. Just because of this line the data is turned to 0, isn't it? So here we transmitted only here. Just because of this line the data is turned to be 0. And that's all. That's why all the devices are going to read 0. So here you can see now all the because of this all the devices are going to 0. So now we achieved half of the part. Half of the part is achieved AND. So this is nothing but AND. So half part we achieved with the wired and the other half part we achieved with AND. So that is about the wired AND. So in case of AND, 0 is the dominant bit. Same thing happens here with respect to the clock. So same thing happens with respect to the clock as well. Now let's update this example. The microcontroller A wants to communicate with temperature sensor, and here microcontroller A is the master. First master will check if the bus is been idle or not. If the bus is idle, in data line you are going to read 1, isn't it? So if it finds bus is been idle, so it will transmit the unique address of the slave, and whichever slave matches with that unique address is going to transmit the acknowledgement, and then the communication is happening. So this is the example. So now wired AND is done, and next is nothing but conditions and validity. In SPI protocol we discussed about the data validity. When is the read happening and when is the write happening. So SPI protocol is the edge triggered protocol, isn't it? But this I2C protocol is a level triggered. So here communication happens with respect to the clock line. At one particular level the read operation happens, and other particular level write operation has to happen. So transmission is nothing but write and reception is nothing but read. So whenever the clock line is being high, all the devices are going to read, and clock line is being low, all of the devices are going to write. So if it is reading, the data will not going to change. Whatever is being transmitted, whatever is being transmitted. So if you are reading the data, then data will not going to change whatever is being transmitted. So you have to read the data as it is. So if the clock is being high, we have to read. So here you can see clock is being high. In that time you have to read. Means here data read. Transition should not happen here. Okay, high to low, low to high. And whenever clock line is high, you are going to write, and here you can see whenever clock line is low, you are going to write. And whenever clock line is high, you are going to read, but there is no transition should happen. But here in this case you can see clock line is high, transition happens from high to low, and here clock line is high, transition happens from low to high. So this is what? So this is the case. This is the case. We are calling it as conditions. So clock line is high and there is a transition from high to low. And here clock line is high, there is a transition from low to high. So if the clock line is high and transition happens from high to low like this, and that is nothing but start condition. Start condition. And if the clock line is high and transition happens from low to high like this, and that is nothing but stop condition. That is nothing but stop condition. So now did you get what is start condition, stop condition? Clock line is high, transition happen from high to low. That is nothing but start condition. And when clock line is low, that is nothing but data going to write. Clock line is high and there is no transition, means data read. And clock line is high and there is a transition from low to high is nothing but stop condition. Now again let's update the example. So what is the first step? Bus idle condition checking. Now microcontroller A wants to communicate with the temperature sensor. First master is going to check bus is idle or not. Then understand bus is been idle. It's going to transmit unique address of the temperature sensor. But if temperature sensor is sleeping to save the power or busy doing some other task, the temperature sensor will be missing its event. Now microcontroller A sent unique address but temperature sensor missing its event. So what is microcontroller A does is, so first it's going to transmit start bit. So before transmit unique address, it will check bus is been idle or not. Then it will transmit the start bit. So it will transmit the start bit. So how it will transmit the start bit? Clock line is high and transition happens from high to low. That is nothing but the start condition. So now whatever start bit is transmitted from microcontroller A received by all the devices in the network. So all devices think somebody transmitted the start bit. There might be possibility of communication happening. Let me pay an attention. Then later microcontroller A transmit unique address of temperature sensor. All the devices are looking to the unique address. So whoever gets matches send the acknowledgement. Now microcontroller received the acknowledgement. It is understood that device is being free and it is ready to communicate. And if it does not receive the acknowledgement, that means microcontroller or master has to understand by default thinking that it might be busy doing some other task. So once the communication done, master is going to send the stop it as well. Then the communication will be terminated. So this is the example. So now we have finished with conditions and data validity, and next is the transmission. So here you can see data on SDA transmission. So there is only one data line, and using that line master is transmitting and slave is receiving, and slave is transmitting, master is receiving, isn't it? So let's consider example. So in here we having PICSimLab, isn't it? So here this is the microcontroller, and this is the master which wants to communicate with the I2C, that is nothing but slave. So now microcontroller wants to communicate with I2C. So in order to do the communication, we using I2C protocol. So now we having master and also we having slave. So master is nothing but PIC microcontroller, isn't it? Master is nothing but PIC and slave is nothing but I2C. So this is the master and this is the slave. So let me write here, M means master and S means slave. Microcontroller is master capable and slave capable, right? That's why I have considered it as master. Now we have two lines here. We having two lines in the master. So one is clock line, that is nothing but SCL, and another one is nothing but data line, that is nothing but SDA. Clock line and data line. Now master is the one who is going to generate a clock line. So that's why the direction should be, let me select this, like this. So from master to slave, and next is the data line. So here it is bidirectional, okay? Because why it is bidirectional? Because communication happens in both the way, but one at a time. And also we need to add the pull-up circuit on both data and clock line. So what we need to add? We need to add pull-up circuit. So here I need to add one resistor. Let me use this. So this is nothing but resistor, okay? So it is not proper. I have not drawn proper. Let me draw like this. Okay, let me do one thing. I'll erase this and I will draw again. So this is what? Resistor. And here also I need to add one resistor. This is the direction, isn't it? So now, yeah, so I'll do one thing. Shit. So assume it is resistor, okay? So now here we have added pull-up circuit, and that is nothing but VDD. I am naming it as VDD. So now microcontroller A wants to read seconds register from RTC. Seconds, not register. So it wants to read seconds from RTC. In RTC there is some registers available and these registers must have some addresses. So there is one register which name is seconds. Okay, now let me write here. So there is one register which name is seconds and address of this register is 0x00. Not only seconds, it are also having minutes register and also having hour register. Okay, and what is the address of this register? That is nothing but 0x02. Not only this, it also having date, then month, year, like that. Calendar also it is having. So these all data is having in the RTC. So that is nothing but what? Registers. So these registers, seconds register who is going to store the seconds inside it, and that must have been present in the address 0x00. And also we having min register, R register, like that. So when master wants to communicate with the slave, what is the first step? When master wants to communicate with the slave, what is the first step it have to do? It should check whether bus is been idle or not, isn't it? That is the first step. Now it will check bus is been idle or not. Now the microcontroller aware the bus is idle. So then what it will do? Transmitting the start bit. So it is the start condition. Okay, then it will transmitting the start bit. So every device is paying attention, including RTC. Next step, microcontroller is going to transmit the unique address. So now whatever microcontroller is transmitted, that have to match that device. That is the third step. Now after receiving unique address, the RTC should send acknowledgement. This acknowledgement is must. Okay. After acknowledging, microcontroller starts reading seconds, isn't it? But RTC is having not only seconds, isn't it? Inside RTC we also having month, year, date. So how it will know to read the seconds or minutes? After acknowledging, microcontroller tell I want seconds. Then master is going to transmit the second register. So master is going to transmit the second register or address. So after that RTC got to know master wants things with respect to second register. But how will RTC know whether master wants to write into the second register or read from the second register? How RTC will know the intention of the master? So when master transmit unique address, it also transmit the intention along with the unique address. So it will send the intention whether it wants to write or read. So usually unique address is nothing but 7 bits. So master is going to send along with the intention, that is one more bit. So that is nothing but intention says that read or write. It says I want to communicate with RTC and I want to read from the RTC or write with the RTC. That will tell master. So when receiving address, it will understand the intention. So master is want to transmit the seconds register address. Now RTC will understand whether master wants to read from the address or write with seconds. Read from seconds or write with seconds register. After receiving second register, there are possibility of receiving an acknowledgement. So this is the possibility, not must, okay, not sure. If master wants RTC, then RTC can give acknowledgement saying that I got to know you want data from seconds register, so it is going to acknowledge the data. Then after that master is going to read the data. So read the seconds. That is the sixth step. It will going to read the seconds. When master is done reading the second, there are possibility of master giving the acknowledgement to the slave telling that I am done. Then it is going to stop the communication. That is the seventh step. It is going to stop the communication. Either it is going to stop the communication or restart the communication. So this is how communication happens between the two devices. And next is the data on SDA signals. So here we having data on SDA. So there is a clock line and also we having data line SDA. So here microcontroller wants to communicate with RTC. Master being the transmitter and RTC is the receiver. First it will checking the bus is been idle or not. Now it aware bus is been idle. And then it is passing the start condition. So how it is passing the start condition? The clock line is high and the transition from high to low happens. And it is pulling the line from high to low. So start condition is being transmitted. Now master is transmitted the unique address and slave is received. Next, master being the transmitter is going to transmit seconds register address. For that master need 8 clock pulses. So it is going to transmit the seconds register address. For that master need 8 clock pulse. So using first 8 clock pulses, master is going to transmit the address of the second register. After it is done transmitting, it pulls the line up. So here you can see it pulls the line up, indicating that it is done transmitting. That time at the 9th clock pulse, receiver has to give the acknowledgement. So this is the receiver. So how it will give the acknowledgement? Pulling the line low. So here you can see receiver giving the acknowledgement, pulling the line low at the 9th clock. It is giving the acknowledgement. After this master wants to read the second, but this acknowledgement is not shown. It is not must. There is a possibility. Okay. So after that, master wants to read the seconds. Now what happened? RTC right now going to transmit and master right now going to receive. So now what is this slave doing? It is going to transmit 8 bit. That means the value of seconds register. Now it is the transmitter and this is the receiver. So master is going to read the data and give the acknowledgement at the 9th clock pulse. How it will give the acknowledgement? By pulling the line low. So after that it will stop the communication. So how it will stop? Clock line is high and transition happens from low to high, isn't it? From low to high. So if you want continue the communication, then repeat start means transmitting an other start bit. It can either be stop or repeat start. And it is stop bit is also called as, also represented by this letter P. Caps letter P stands for purge. So here you can see P. So Philips represented it as P. Okay. So this I2C protocol is developed by the company Philips. Now it is given this name P. So here you can see this data line having transmitter, receiver, like that. So this slide shows with respect to transmitter, receiver. But in actual there is only single data line. So here you can see SDA actual. So this is the actual line, actual signal who are going to see at the data line. So actual SDA shows the AND operation of these two lines. So here you can see AND operation of transmitter and receiver. So here it is 0, then it is 1. That is AND operation of this is 0. Data and 1 is nothing but data. 1 and 0 is nothing but 0. Okay, this is the AND operation. We preferring only this line. Okay, this is about the data on SDA, and next is the signals clocking on SCL. So that's all about today's session. In the next session, let us discuss about the clocking on SCL. Thank you all.